so I'll just jump in. So the presentation's kind of split into two parts. The first part describes computer networking as a domain, and then the second part we talk about how we try to tackle the complexity of the domain using HVM. All right, so sorry for those people who already know about this stuff, but just in the interest of getting everyone on the same page, I'll start off with just describing computer networks. So a computer network is a collection of devices which communicate over a shared medium. So think about physical cable or Wi-Fi using radio frequencies using agreed upon rules. So that's what we call communication protocols. At the heart of modern communications is a logical identifier that is called an Internet Protocol address or an IP address. And when a device communicates with another device, it crafts a message with its own IP address as the source and the remote device as the destination address, and sends it across. So let's just talk about a simple example of yahoo.com. I had to pick Yahoo because google.com, they were being clever and it actually resolved into somewhere in Australia. So I had to pick something that's not in Australia for this example. But let's focus on the first few lines. So through the power of the domain naming system, we have yahoo.com, which gets resolved to 74.6.231.20. And that's the destination that we want to send our message to. That IP address is located in Nebraska. And I want to kind of highlight this because it's going to be important later, but there is a notion of an ASN, and that ASN owns this IP address. And interestingly, the IP address for yahoo.com is not owned by yahoo.com. It's owned by this Oath Holdings company. So we'll come back to this later. So connecting to yahoo.com, we start off from my computer, and we go 17 devices through till we reach number 18, yahoo.com. And on the way there, the message that I've sent, or the packet that we say in this kind of parlance, that packet starts off from my computer and from point to point goes to each of these devices. So it gets routed by these devices in between, and each device kind of sends it off to the next device until it reaches yahoo.com. That device is called a router. So the router itself, all its job is to do is to route, and it's got when it receives a packet, it looks up the destination in its routing table to determine what the next router is, which it sends the packet to. So this is repeated by each router until the packet arrives at its destination address. So routers come in all sizes. I think everyone kind of recognizes their home router, which connects them to the internet. But we have kind of small office routers as well, a little bit bigger, and we can go up to carrier grade routers. So this is the routers that are run by your ISP. So think, British Telecom or Telstra in Australia, big routers that can take a lot of traffic, and these can go up to hundreds and thousands of dollars, even millions of dollars, these devices. Through iconography, though, we represent it as this device, which is kind of representative in networking diagrams everywhere as a router. Okay, so let's kind of take a little peek under the hood to see how a router works. So there is a static component. The router is configured. It's given a name because we like names by network administrators, but there is also a dynamic component that participates in the local network and sharing information about itself with other routers. So I did mention that the router looks up the destination of an incoming packet in its routing table. So this routing table is dynamically generated by exchanging topology information with its neighbor routers. In technical term, this topology information is called the routing information base, or RIB. And once this information is collected, it distills from the RIB a routing table called the forward information base, or FIB. So this is kind of a diagram of under the hood what's actually happening. So there's a dynamic component, which is the RIB, and then the FIB is what's used to forward packets as they come in. One kind of thing I do want to mention is that this is a dynamic process. So say we have the first packet, it arrives and then leaves. When the second packet arrives, it could be going to the same destination, but because of a change in the network, maybe a router has gone down, maybe something else has happened, the RIB dynamically regenerates and then creates a new forward information base, and the packet could leave a different interface. So in the space of a few seconds, the packet could be going in a different direction. And this was by design when routing was kind of invented. In case of a catastrophic failure, so a nuclear attack, the information network would automatically reconfigure itself to stay resilient. All right, so the internet. So we're going quickly to get to modeling pace. The internet is made up of routers. So here at the bottom level, you can see that you start off with IP addresses, which belong to a router. And at the top level, each router belongs to an autonomous system. So this autonomous system is geographically bound, and it is, you have a few autonomous systems. Generally, internet service providers are autonomous systems. They own IP address space, and they have geographic bound. But universities can be ASs. Any large organization that participates in internet routing will have an autonomous system number. And that goes back to the Yahoo example when we talked about Oath Holdings being an ASN. CADIA is an organization that attempts to kind of map the visual complexity of the routing space. So this is a picture from 2020. And if we zoom into one kind of segment of it, we can see that each box on this diagram represents a router. And so in the core of the network, it's taking a lot of bandwidth, a lot of packets are going through, and as you go closer and closer to the edges, you're going to kind of a local distribution of that. So, and that's all different organizations that contribute as part of the internet fabric. So to illustrate kind of the information requirements that we have in the networking domain, I've kind of highlighted two case studies for that. The first case study is Google. So everyone's heard of Google. They run planet-scale networks across the world. And so they need network automation for the different network management phases that they themselves have to maintain, such as design, deployment, configuration, and the day-to-day operation. And you can see by this world map that the Google infrastructure is like all across the world, and they have their own autonomous system number as well. Google themselves have embarked on this project to develop a multi-layer abstraction topology for networking, and there's a great presentation about that as well if you're interested to learn more about their approach. The interesting kind of thing about this exercise is we ended up with, Al and I ended up with like very similar kind of entities and identities, even though we started from very different approaches, which is quite impressive as a kind of modeling paradigm. So Google themselves, they have a requirement to forecast bandwidth demand in their data centers, do network designing from different layers, from different perspectives, and configure various different vendors from one single source of truth. And this is a snapshot, picture from their paper that they published about how they've done it, and they've kind of done it through an entity relationship graph. So they found relational databases to be too constrictive, and they've gone with a relational graph, and this is their approach. So my second case study is kind of cyber defense perspective. I come from a cyber security background, and so Salt Typhoon is what we call in the industry an advanced persistent threat, an APT. And initially they were detected against activity against several US telecommunication providers in late 2024. Microsoft has attributed them, and they've called them this actor called Salt Typhoon, but attribution, like on paper it's China, but well, actually not on paper it's China, but it's all indications point to China. and so Salt Typhoon use their access into telecommunication providers to snoop on US lawful intercept targets and intercept the communication of significant political figures. So there is definitely a security perspective on why information record keeping and building information systems is really important. As you can see by the world map, they have targeted predominantly US, but lots of other countries as well. And there's been lots of newspaper, well, not news articles about Salt Typhoon themselves. And a lot of the information for this presentation was taken from the Cisco Talos blog post. So in the context of cyber defense, Salt Typhoon, to conduct their operations, basically use two different vectors. One was publicly available vulnerabilities, and these in cybersecurity we call them CVEs. And so you can see by their dates that although the activity was December 24, they've utilized vulnerabilities that were in the public domain for a long time, and so could be patched but were not. They also modified device configuration. So as I mentioned, routers have a static component. So that's the component that the administrators configure. And that is a lot of kind of information about the functionality of the device. There is also a dynamic component, which the kind of attackers really can't interfere with too much. But this, the static pieces are represented in a configuration like this. So this is an example of a Cisco configuration. And you can see like elements like here we've got this GRE tunnel. And so this would be something that the attackers would type into the routing configuration terminal and change the configuration. Internally, a lot of the providers, they will track this configuration files as text. So there's a lot of tooling for managing and backing up the configuration files, but they don't have any notion of linking that text to information records. So I'll go into that a little bit, but it's to highlight, like, if we don't, if an administrator sees permit TCP any equal 23, they're like, oh, okay, that looks all right. There's no context to be like, who put it in there? What does it actually do? What does it mean? That context and the semantics are not in the configuration. You can point to it if you're an experienced network administrator, but inherently it's not in the text itself. And that was important for the modeling piece. So here I've kind of combined the two case studies together, and we talked about some information requirements that one would need and what you would need to model in the network domain. So as I said, routers have names, identifiers, their host names. Google themselves would have this utilization over time, and each interface, each port on the router itself would have statistics to help them with that information. Vulnerabilities, assets in the field, that is just understanding what you have deployed, and then you can make the query if it is susceptible or not to vulnerabilities. The notion of a provision service, so a lot of routers are there for other customers. Business customers can pay for special kind of services that the telecommunication provider can provide. And that, as what we saw, was the GRE tunnels, but there's other types of identifiers that the telcos can provide. There's also the notion of IP addresses, obviously, that's key. And the changes to the physical nature of it, so what's it connected to, we would also have to map the physical connections. So just a note on the physical connections. Here's kind of a picture that I've just taken from Google about two routers. A router and a computer server. So this is kind of racked up in a data center somewhere. This is kind of how computers look like in the real world, a bit gross. And so very simply, we would, although in a representation like on a diagram or something, we would have a router connected to a computer. In reality, there's a lot of complexity that's going on. And Google raised that complexity in their slide deck when they were presenting about their MALT project, that connections are physically and functionally quite complicated. So, in my picture, I have just a single line representing that connection, but that connection could go over various different transport mechanisms, various different, changing between the nature of the line. It could be electronics, then it could go optical. So the network domain model has to represent complexity. All right, so on half time. So the next part of this talk is about how we actually modeled IP routers using HQDM. All right, so HQDM was one of the things we did was, it's a 4D. I mean, I don't need to go too much into it. Everyone should be might have heard of it already, but the challenge was to model network entities within the network domain, which was stable over time. So time is a very important facet of networking that in my work has to be kind of a first-class citizen, and that's why I was attracted to 4D representation, because time is a first-class kind of entity. So entity is the wrong word, but you know what I mean. So there's core patterns that makes modeling this kind of decompose quite nicely. We have a system and system component, associations, and representation by sign. So for system and system component, each part could be modified, upgraded, or removed without changing the identity of the router itself. And that's really important for changing of line cards or physical components, that the router itself is still the same, but the components which may be important for, say, vulnerabilities or lifecycle management, they can change independently of the device itself. Using association and representation by sign, it was possible to represent IP addresses and other things that appeared in the configuration as signs. So this, going back to the example from Salt Typhoon, we had a lot of pieces of the configuration file that are signs and that are associated to the physical components. And so using those two patterns, we could quite comprehensively model most of the configuration file itself. So just with 3 simple kind of patterns, we could decompose the problem. We use Magma Core as a kind of a way to bootstrap the modeling process, which generated the RDF that you see in the slide. And so now we'll talk about some space-time diagrams because, we'll talk about some diagrams which kind of are representations of the RDF in a visual representation. So we start off with the router, which exists for a period of time. One of the really great things of having system component is the ability to model the space, like the line card that the slot of the line card, which exists over time. You can see here in the router it exists, but the state of the line card, which is installed and uninstalled, can be represented as well. So if the router components change, we can model that accurately. One router is a bit boring, and so every network has at least 2 routers. Or I mean, not necessarily, but 2 routers make it interesting. So we've added another router in. I mentioned the representation by sign. So having something, we had a config that had the hostname of retail. Retail is used by the config to represent the state of the router at a period of time. And so when people talk about routers or they talk about networking, they very much think about hostnames first. And so we wanted to kind of have as a way to, like, when we talk about the state of a router, the state of the router, that hostname is used for that period of time to represent that state. Now, the router itself, the hostname is a string. So you can see here it's retail1, but it also has a community that kind of recognizes its use as a hostname in this process. And in the like networking domain, the Internet Engineering Task Force, the IETF, produces RFCs. And so the earliest RFC is called Request for Comments. The earliest RFC that I found referencing how hostname should be created, what's a valid host name, is from 1995. So, sorry, 1985. So from the Department of Defense. So there's been a lot of RFCs in between, but we can actually, if we need to, represent that community that recognizes that host name as a valid host name, apart except like as opposed to like a name of a shop called Retail One, as in HQDM as well. Here's some more kind of representation of router 2 as well, with the same recognizing language community. So going to IP addresses. So IP addresses in a network config. So here's an example of that snippet. The part highlighted in blue is the IP address itself. That is a sign. It references in the configuration. It's a sign. It's a string. And so what we want to do is just associate that sign to that physical kind of line card and that port. So here in this example, we've got a module that gets installed in a line card, which then is installed in a router, which the IP address is associated with. And in that way, we've accurately represented everything we know about what the config is telling us. So that was another kind of, we'll have a summary at the end, but one of the key kind of learning things that I've learned through this process is only modeling what we know. It sounds kind of obvious. A lot of these things sound obvious, but it's, oh no, that's not great. Yeah, one of these things sound obvious until you do it. Sorry, I think I have to go, whoop. Oh, yep, so we got IP address, yep, okay. So here we've got this representation. The config, routing config you see is on the right. It lists all these configuration that a static configuration that the network administrator would type up. That is that configuration has an association with the state of the router as well. So with these things, we can link different parts of the provenance, the sourcing of this information, all in one model, with preserving time. Functional items themselves, like line cards and things, can also be installed, and they're installed for a part of time. And we can also decompose. So the line card will have multiple ports. Those ports sometimes can be, so like for optical ports, for example, can be installed and removed. And so this is what that QSFP module is. It can be installed in a line card. This can scale quite well, and it looks like a lot of information, but what this says is like a line card with 27 ports, all can have an individual QSFP installed as well. Physical connections. Now, right at the beginning, we spoke about kind of decomposing that connection. So in a lot of network diagrams, you'll have a router and a device with a line between it. That line itself hides a lot of complexity, the abstraction hides a lot of what's actually happening under the hood. And as that Google slide showed, that complexity has to be dealt with at some point. And so we've also modeled connections between routers in HQDM as well. And that ability, we can also, if we step back from the user perspective, because like I feel like generally if we're showing space-time diagrams to users, we've lost. So the idea is that we would present a query interface. So this was, I mean, most of the hard work was Al, but he had a very nice way of generating mermaid diagrams, which programmatically generated kind of connections between routers at a certain point in time. So here's a comparison with in April 23, there was a connection. In May 23, host name has changed, still connected, and in October 25, the host the router Retail 2 is no longer connected to the router Retail 1. So here you could see that the host name has changed, but the router identity has been preserved and still disconnected. So this is quite important for tracking customers, but also tracking how the network changes over time as well. So if you're planning for bandwidth or expansion, this is actually quite important. This scales up quite well, and it's going again highlighting the power of using certain core patterns, where we could use 3 simple patterns to represent the complexity of all the things that we cared about in the networking domain. So in conclusion, like my experience in modeling work, this was my first kind of foray into 4D. I'm quite a big fan of it now. I'd like to say I'm an enthusiastic amateur. So definitely all of the kind of formal thinking and modeling has been Al, really. So he's been quite generous in letting me present, but it's definitely both of us working on this. My background is networking and computer security and engineering. And so trying to model kind of stably over time what computer networks actually mean and what it means for information requirements for my use cases in the security domain was quite insightful and enlightening. So I think these are kind of my conclusions of what I've learned. But understanding the information requirements before you begin is key. And I had to really clarify that as working through the problem. There had to be a stopping rule, and that for Al and myself was like analyzing only what's known. So when you look at a configuration file, it's very tempting to say, oh, the IP, the interface has a description, and this description says it's connected to router 2. So therefore, it's connected to router 2. That is definitely a trap in thinking. Because at that point in time, you actually don't know any more than what is right in front of you. So to the more experienced network or more experienced ontologists, that's like quite simple, like it's self-evident, but this is the stuff that I learned in the process because it actually leads to inconsistencies. Focusing on the physical aspects, it really helps with the ground, the model development. Most of the domain complexity could be decomposed with a few model patterns, allowing that model to scale quite well. And this approach that we've taken degrades quite gracefully and goes beyond the current industry best practices. So this is kind of the last slide from the last few, sorry, it's actually the beginning, but it talks about the information requirements that Google has identified. And so connectivity, address allocations, routing policy, we need precise and accurate data to do all of those things. And we need like the same kind of information needs that they've come out. We've also reached from a very different perspective. And so it talks about the whole life cycle, not just a point in time, like in totality. We need like low-level abstraction to deal with the complexity of the domain. And we need that ecosystem to build and develop and test these models in as well.